Namaste and welcome to yet another lecture on linear algebra through geometry. In the last module we looked at the idea of vector spaces, vector subspaces, linear combination of vectors in a higher dimensional vector space, and we looked at what it is to say a set of vectors to be linearly independent, and we also looked at what is called as the basis for a vector space. That is basically a set of linearly independent vectors whose linear combination gave us all possible vectors in the vector space. So, we looked at the basis for a vector space, and we also looked at the idea of unique representation of a vector if in a given in a vector space in any given basis. So, if you have a basis for a vector space, then any vector from the vector space has a unique representation in terms of this basis. That is what we saw, and we also saw the idea of orthonormal basis. When you had orthonormal basis, the scalars are easy to pick when you want to basically write a vector as a linear combination of these orthonormal basis vectors, because you just had to do a dot product, and you could get the dot product of the vector with every component. You ended up getting the coefficients very easily, and prior to that we also proved that the set of orthonormal vectors will be linearly independent set, and that is exactly why we took that to be a basis for a given vector space and so on. And then we looked at the idea of the dimension of a vector space. The dimension of a vector space or a vector subspace was basically the number of elements in any basis, and we also found out that every basis for a given vector space will have the same number of elements, and we looked at a very specific case of the vector space being the one which contains just the 0 vector. And in that case we also saw from our idea of linear independent set of vectors, any set of vectors which contains the 0 vector is a linearly dependent set. We saw that, and therefore this subspace which contains only the 0 vector, there was a problem because the only vector which was present there was the 0 vector, and we wanted a linearly independent subset of the subspace. A linearly independent subset of the subspace is basically you remove the 0 vector from there, what you get is your empty set, and that empty set is therefore what we called as the basis for the vector space which contained just the 0 vector. And when we looked at the dimension for this space, we said that the dimension of the vector space which just contains the 0 vector alone, or the trivial subspace, was 0. So, and then we also looked at the geometry of the various vector spaces that we could have, subspaces that we could have of a vector space. We said that if you look at Rn, you can have the set containing just the 0 vector was a trivial subspace, entire Rn was yet another subspace of Rn itself, and we looked at set of lines. We looked at we also said that look, any line passing through the origin in Rn is a vector subspace of Rn, any plane passing through the origin in Rn is basically a subspace of Rn. That is also that those are things that we have seen. Now what are we going to do, where are we heading to? So what we are going to do now is we are going to revisit our system of equations, and that is exactly where something interesting happens. We are going to revisit our system of equations idea and try to figure out if we can kind of get together the ideas that we studied in terms of system of equations, solutions to the system of equations, to that of the geometry that we have studied, especially in terms of the subspaces and the vector spaces that we have looked at. So this module is going to focus on the 4 fundamental subspaces associated with any matrix A, and we are going to look at the geometry, and then we are going to look at the dimension of the 4 fundamental subspaces, and we are going to define the rank of a matrix, and so on, and we will also look at subspaces which are very specific to a certain kind of matrices, and the what you call vector space which allows us to use a special operation like the inner product. We are going to have different kind of subspaces. So, we are going to look at all that in this module. So, in this lecture what we are going to do is we are just going to look at solving system of equations and try to understand a few things, and in the next lecture we will formally put all these ideas together to actually say that look, yeah, geometrically we have seen that something happens here, algebraically we will prove that it actually holds good. That is exactly what we are going to look at, right. So, let us get on to our lecture. We are going to look at solving system of equations and go ahead with that. Okay. First of all, let us I mean this is the most what do you call this problem that I am going to write now is something which we have been seeing almost everywhere whenever we looked at this 2 dimension, though it is like most used, misused, abused system of equations that we are going to look at. We are going to, because that is going to help us understand things better, right. Let us consider this. Okay. What is that? Consider two x1 plus x2 is equal to 0, x1 plus 2 x2 is equal to 0. This is our example 1, and alongside I am also going to consider a second example where I am going to look at this example 2, 2x1 plus x2 is equal to 0. Second equation is also say 2x1 plus x2 is equal to 0. I am going to look at these two examples, and of course we will take up any general matrix, a 3 by 3 also we will take after this, and then we will look at any m by n matrix, right. So, let us look at this. So, I want to look at the solution to this system of equation. Solution to the above. If you try to solve the system of equation, we already know that x1 is equal to 0, x2 is equal to 0 is the only solution to the above. Right. That means what am I going to say? I am going to put this, I am going to say suppose I call this solution, let me define, let us put let us give a notation for this, let NA be the set of solutions to Ax equal to 0, right. In this case what will NA contain? NA will just contain this vector 0 comma 0 corresponding to my solution, which is x1 is equal to 0, x2 is equal to 0. This means I am going to write this as, let us say if I put it in matrix format, I am going to get this 2 1 1 2 into x1 x2 is equal to 0 0. So, the only solution to this is x1 is equal to 0, x2 is equal to 0. What we see is the only vector 2 component vector, that means the vector in R2 which gets mapped to the 0 vector by this transformation A is just the 0 vector, and that is the solution to the system of homogeneous equation that we have had, right. Let us look at this, let us look at this case where the solution to the above is basically what, let us look at that. So, what does it say? It says 2x1 plus x2 is equal to 0, 2x1 plus x2 is equal to 0. So, we can say that I mean if you try to solve this, we get x1 is equal to 1, x2 is equal to minus 2, yeah, 2 minus 2 gives me 0, and this is basically what we see is a non trivial solution to Ax equal to 0. Yeah. Now it is not just 1 comma minus 2, let us write all that, let us write a set of points which get I mean which could be the solution for this. So 0 0 is definitely a solution, because we already know that the homogeneous system of equation has the trivial solution to be existing at all times. So I am going to have 0 comma 0 to be the solution, then 1 minus 2 is a solution, minus 1 2 is a solution, right, minus 2 plus 2. So you have then 2 minus 4 is a solution, minus 2 4 is also a solution, and so on. That means what we see is the any multiple of, let us look at this, any multiple of this vector x1 x2 is equal to 1 minus 2 is a solution to is that right? So on the one side we see that only 0 0 is the solution. On the other side what we are going to do is, therefore I am going to write again NA for this, that means the set of solutions here. So I am going to write NA to be what? This is nothing but scalar multiples, let us say k times 1 minus 2, where k is real, this is what we are going to have. Yeah. So this is basically the set of all possible solutions to this equation. That means I am going to have NA to be equal to k into 1 minus 2, k is in R. Yeah. So there is something interesting that comes out here. What is that? Suppose if we try to look at the geometry of this solutions to the homogeneous system of equation that we have here, the one which we had like 2x1 plus x2 is equal to 0 and x1 plus 2x2 is equal to 0, and the other side if we try to look at the geometry of this, we see something interesting coming out. Let us look at what it is. So in this case if we take NA, we just have this vector 0 0 alone, and this vector 0 0, this is basically, this vector 0 0 is an element of R2, is that right? It is an element of R2, it is an element in R2, and that is the only solution to this, and we know that it is a subspace, is that right? So it is basically a subspace of R2, and in fact it is the trivial subspace. So what am I going to say? I am going to say NA in our case, in the current case, NA for okay, NA in this case. What is this case? The A corresponding to this matrix 2 1 1 2 is the trivial subspace. On the other side when we looked at it, NA, let us try to see what is the geometry of this that we get. So let us look at this 0 1 2 3 4 5 1 2 3 4 5 minus 1 minus 2 minus 3 minus 1 minus 2 minus 3. So let us have this 1 2 3 4 5 1 2 3 4 5 minus 1 minus 2 minus 3 minus 1 minus 2 minus 3 minus 4 and so on. So what are the set of points that we have? We had this point 0 0 which was already there, then we had 1 minus 2 which was here, I hope that is correct, 1 minus 2, then we have minus 1 2 which is basically here, then we had 2 minus 4 which is going to be somewhere here, and then we have 2 minus 2 4, and then we are going to have 2 minus 4 here. What is it that we get? What is the geometry that we get? The geometry is basically a straight line passing through the origin. That is pretty interesting, because so this is basically what on this line, the points on this line are basically the solutions to the homogeneous system of equation corresponding to the matrix 2x, the system of equation 2x1 plus x2 is equal to 0, 2x1 plus x2 is equal to 0. And what did we see before? We saw that any line passing through the origin is a vector subspace. Therefore, what we see NA in this case, which is basically the set of multiples of this point 1 minus 2 of this vector k real, what we see is also a subspace, is a subspace of R2. Right. Now, let us see if something similar that happens in 3-dimension case. Let us look at a couple of examples and then see if this happens, and we will also take a matrix which is not a square matrix. Basically, we will look at a rectangular matrix and see what happens, and then figure out how is it going to look like. We want to look at the geometry and see if all the excitement that we had in the previous slide, where we looked at the set of solutions to the homogeneous system of equations being a line passing through the origin, and that the origin itself, let us see if that excitement still remains, or if something bad happens in higher dimension, let us see if we can generalize results accordingly. Okay, so let us look at this. So let us take a example. Let us consider this example where I have x1 plus x2 plus x3 is equal to 3, x1 minus x2 plus x3 is equal to 1, and let us take 2x1 plus 2x3 is equal to 4. I have this, right. Now, if we try to solve the system of equation through I mean we will not even take this. Okay, I should not have looked at 3 1 4. Instead, let us take all of them to be 0. We will come to that right hand side not being 0 at a later point of time. We will take all of them to be 0. Let us see what is the solution to this system of equations. So, solve. So, what do we get here? We have this matrix which corresponds to 1 1 2, 1 minus 1 0, 1 1 2 into x1 x2 x3 is equal to 0 0 0. So, we can look at the solution to this. We can very clearly, I mean we can do the elementary row reduction, and we can see something here. So, I will do this. I will say R2 is R2 minus R1 and R3 is R3 minus 2 times R1. So, I have this which is basically 1 1 1, this is 0, 1 minus 1 is 0, and that is 0, minus 1 is minus 2, then 2 minus 2 is 0, 0 minus 2 is minus 2, and then 2 minus 2 is 0, right. Now, what I do, I am going to do from here, I am going to take R3 is R3 plus R2. I am going to do R3 plus R2. So, what do I get? I get 1 1 1, 0 minus 2 0, 0 0 0, right. And what we have here, x1 x2 x3 is equal to 0 0 0. This is what we have, right. Now, if you solve the system of equation here, what do we get? So, in this case we see that x3 can be any value. Let me take s3 is equal to some s, that is a free variable that we have. Then we have the second equation which gave us minus 2 times x 2 is equal to 0, we have minus 2 times x 2 is equal to 0, which implies x 2 is equal to 0, and sorry, the first equation which said x 1 plus x 2 plus x 3 is equal to 0, x 1 plus x 2 plus x 3 is equal to 0, we have x 1 plus 0 plus s is equal to 0, which implies x 1 is equal to minus s. Therefore, the solution to this, the solution to Ax equal to 0 is basically this x 1, x 2, x 3 is equal to minus s 0 s. I can write this as my s into minus 1 0 1. Now, what is again interesting is you see that if I keep changing the value of s, right, if I keep changing the value of s, I get different values. Say for example, I take this as 2, minus 2 0 2, minus 2 0 2 is a solution to the system of equation. Then if I put s is equal to 3, I get minus 3 0 3, that is also a system of solution to the system of equation, and this is basically multiple of a single vector. Therefore, what is Na going to be? Na is going to be s times minus 1 0 1, is that right, where s is some real number. We just saw some in the previous module that if you just have only one linearly independent vector, which is basically this, and this is all, rest of the vectors are multiples of this vector, this is again going to be a line through the origin in R2 R3 in this case, right. This is going to be a line through origin in R3. Therefore, we are going to say Na is basically a line passing through the origin in R3. The set of solutions basically that we have is to the system of equation is basically a line passing through the origin. Oh, that is very interesting. Why? Because again any line passing through the origin is going to be a vector subspace. Now, let us take one more case and then see if we are able to make sense out of this. Let us take a second case, I mean another example, where I am going to have x 1 plus x 2 plus x 3 is equal to 0. I am going to have x 1 plus x 2 plus x 3 is equal to 0, 2 x 1 plus 2 x 2 plus 2 x 3 is equal to 0. Yeah, this is what I am going to have. So, if I do the row reduction here, I am going to get this RREF. If I obtain the RREF, I will say that R2 is R2 minus R1 and R3 is R3 minus 2 times R1. So, I am going to get this 1 1 1 0 0 0 0 0 0. This is what I am going to have, and finally I have this x1 x2 x3. This is going to be 0 0 0. Now, from here we see that x2 and x3 are free variables. So, I will take x2 is equal to s and x3 is equal to t, and what we have x1 plus x2 plus x3 is equal to 0, which implies x1 plus t plus s is equal to 0, which implies x1 is equal to minus t minus s. Therefore, the solution to this system of equation is basically given by x1 x2 x3, which is equal to minus t minus s, s and t. This I can write this as t into minus 1 0 1 plus s into minus 1 1 0, right. And if I keep changing t and s, I get different vectors, and we see that these vectors minus 1 0 1 and minus 1 1 0 are linearly independent vectors. So therefore my NA, which is basically the system of the solution to the system of homogeneous equation that we have here, is going to be this set of vectors, which is nothing but S into minus 1 0 1 minus 1, let me just put that, minus 1 T into minus 1 0 1, yeah, T into minus 1 0 1 plus S into minus 1 1 minus 1 1 0, and T and S are real numbers. Now these two are two linearly independent vectors in R3, and what does that give me? What is the geometry that I am going to get out of this? The set of all those vectors which are going to be linear combination of these two linearly independent vectors, it is going to be a plane passing through the origin. So NA in this is going to be a plane passing through the origin, defined by plane passing through the origin defined by this, what is that, the linear combination of that vectors T into minus 1 0 1 plus S into minus 1 1 0, ST real, right. Now this also is now a subspace that we see. A plane passing through the origin is again a subspace of R3 here, right. So in this case also I see NA to be a subspace of R3, right. Now suppose if you take another example, I just wanted to cover some examples before we actually take up the entire proper math proof and other things. So I just wanted to visually give you certain this one. Let us take the next example. So I have x1 plus x2 plus x3 is equal to 0. I have x1 minus x2 plus x3 is equal to 1. Then I have x1 plus 2x2 plus 3x3 is equal to 6, right. If you try to do this row reduction on this, you will end up seeing, oh sorry, again let me put this as 0 0 0, I should be okay, 0 0 0. I am looking at the homogeneous system of equations, so for naturally this has to be 0 0 0, I hope I put this as 0, yeah, 0 0 0. If you try to look at this, the only way in which you will get the only solution to this is, solution is NA is equal to just the 0 vector. This is again a subspace of R3, is that right? This is just that subspace which contains, this is the trivial subspace. So this also the set of solutions for this homogeneous system of equation, that also forms a subspace, be it in 2D or be it in 3D, we are able to figure it out. Now what I do is I will take another example where I am going to look at this case. Let us take this example where I have A, okay, let me not write this. So let us have this case, 2x1 plus x2 is equal to 0, x1 plus 2x2 is equal to 0, x1 minus x2 is equal to 0. Yeah, I had okay, let me make it a bit easier. So let me take this. Let me take this x1 is equal to 0, x2 is equal to 0, and let me take x1 plus x2 is equal to 0. Yeah. Now what does A correspond to here? A is the matrix which is 1 0 0 1 1 1, and what does it do? It basically takes a 2 component vector. That means this matrix is going to take a vector from R2, and it is going to do something interesting. It is going to take this vector from R2 and going to give me a 3 component vector which is 0. Yeah. So, this is basically a 3 by 2 matrix, this is a 2 component vector and that is going to be a 3 component vector, right. So, this is what we have. Now, if you look at the solution to this, the answer is already there. The solution to this is x is equal to x1 x2 which is 0 0, that is the only solution that we have. And if you look at NA for this, it is again just the 2 component 0 vector and that is a subspace again, right. Let us take one more, let me put it this way, let us take a second example, x1 plus x2 plus x3 is equal to 0, x1 minus x2 minus x3 is equal to 0. Let us take this. Now, what is the matrix A? I am going to again look at the system of equations in the matrix form. I have 1 1 1, 1 minus 1 minus 1, and what is this going to do? It is going to act on a 3 component vector 1 1 1, 1 minus 1 minus 1 is going to act on a 3 component vector, say namely x1 x2 x3 to give me 2 component 0 vector. Now, if I try to do the RREF for this, I can take R2 is equal to R2 plus R1. So, for which I will get R2 minus R1, let me take R2 is equal to R2 minus R1. So, I get 1 1 1 0 minus 2 and then minus 2. We have x1 x2 x3 is equal to 0 0. Yeah. Now, if you look at here, the pivot is there only in the second row, x3 is basically not a pivot variable, therefore, x3 is a free variable in this case, x3 is free variable, that means x3 can take a value let us say t, then we have minus 2 x2 minus 2 x3 is equal to 0, which implies minus 2 x2 is equal to 2t and x2 is equal to minus t, and the first equation says x1 plus x2 plus x3 is equal to 0, x1 plus x2 plus x3 is equal to 0. So, we have x1 minus t plus t is equal to 0, which implies x1 is equal to 0. Let me just check, x1 plus x2 plus x3 is equal to 0. So, we have x3 is equal to t. So, we have this. So, x1 is equal to 0. Therefore, the solution to this solution is NA is equal to what is the solution that we have? We have 0 minus t, I can take this as t into 0 minus 1 1 t real number. Now, this is one linearly independent vector that I have, and the multiples of that is going to be a line through the origin in R3, and that again is a subspace. Therefore, what have we found? We found that the set of solutions to the homogeneous system of equation Ax equal to 0 will always be a subspace, and that subspace is what we call as the null space of A. So, let us write this set of, okay, let me write this. Okay, set of solutions to Ax is equal to 0 is a subspace, and we call this subspace, as the null space of A. As the null space of A. So, let us make it a bit more general before we wind up. We are going to say that if A m by n is a real matrix, okay, I let me make this, let A m by n be a real matrix, look at the homogeneous system of equations, genus system of equations Ax is equal to 0. Now, the solution to Ax equal to 0, that is, okay, let me put this, the set of all x now we have taken A to be an m by n matrix. So, this is going to be m by n, this is going to be an n component vector and that is going to be an m component vector. So, what we say, set of all x in R n such that Ax is equal to 0, right, the set of all x in R n such that Ax equal to 0 is called, let me write, is a subspace of R n, because x comes from the x vectors come from R n, it is an n component vector, is a subspace of R n and is called as the null space of A. Denoted by N A. That is nice. So, we found out that associated with a matrix is associated with a matrix say A m by n, you always have what is called as a null space, which corresponds to the set of solutions to the homogeneous system of equations Ax is equal to 0. That is a null space, and this set of solution, that is the null space, basically is a subspace of R n. We have seen geometrically that these are basically the lines passing through the origin, or just the trivial solution, which is basically, or just the trivial subspace that you have, or it is a plane passing through the origin. And we already know that line passing through the origin, plane passing through the origin are all subspaces of a higher dimensional vector space. Now, what we are going to do is, when we come back for the next lecture, we are going to look at proof, a mathematical proof for this, saying that okay, it is indeed a subspace, right. And there are 3 more fundamental subspaces associated with a given matrix A. We will look at all that in the next lecture, and we will also look at the dimension, because we have told that there is this, because we have said that there is going to be this subspace, every subspace has a basis, and the number of elements in the basis is what we call as dimension. We are going to look at all those things together, and we are also going to look at some special subspaces that are associated with a matrix. I mean, in the sense, if you take a square matrix, we have this idea of eigenspaces, and in case of any of the matrix, if I incorporate this inner product, I also get what is known as orthogonal complement subspaces. So, we are going to look at all that, and towards the end of this module, we will see how are these 4 subspaces oriented in the sense, what is the, I mean, since we talk about geometry, we are going to say that okay, do they have any relation, or they do not have any relation at all, in the sense I mean this kind of orthogonality that we spoke about between vectors, we are going to look at it in terms of even the subspaces. So, that is something which we are going to look at in the subsequent lectures that we are going to have. Thank you.